Hello, welcome to my first video in the new playlist that's devoted to topic 5 in the FRM. Topic 5 is the first topic in part 2 and it's market risk. And so we start here by comparing normal to log normal VaR. And specifically, we're going to generalize to absolute VaR. So that's why I've got a little A there. Absolute VaR generalizes the relative VaR. So it's the complete version of VaR. But the key things we're going to do here is look at 4 different use cases so we can compare normal VaR to log normal VaR in the single period case. Normal is when we assume that the arithmetic returns are normally distributed. Log normal is when we assume that the geometric returns are normally distributed. And there's going to be a specific advantage to using log normal that I'll show you. And then I'm going to do the same thing, compare normal to log normal, but we're going to scale it over time. We're going to be given 1 month assumptions and then scale to a 1 year VaR in both cases. Finally, we'll apply this to a GARP practice problem from its practice paper 2017 part 2 question 2, which gives us some assumptions and will require us to compute both the normal and log normal VaR by scaling down per annum assumptions into 1 day VaRs. So I look forward to sharing this. So I'll start with the simplest use case, and that's a single period normal VaR. In this case, we're going to assume that arithmetic returns are normally distributed, and our VaR then is given by negative Greek mu. That's the drift or expected return. Right here, I'm using 1%, plus going in the other direction, we'll take the volatility, denoted by sigma, of course, multiplied by normal z. That's the normal deviate or normal quantile that's associated with some level of confidence. So not a bad idea to subscript this with an alpha, just to be explicit about the fact that this really scales based on the user's preference or selection for the confidence level. And so because we're assuming arithmetic returns are normally distributed, then this is a z or normal deviate, and our 2 most common use cases, especially in exams of course, are 95 and 99%, so that you certainly should memorize that the 95% confidence for this normal distribution associates with 1.645. On exam, it's fine to round this out to 1.65, very common to do that. And for 99%, of course, that's 2.326, very common to round this to 2.33. And of course, these are normal deviates, but they are one-tailed, right? So 95%, if I go out here to this quantile at 1.645, then I have area to the left. It's a cumulative distribution function, or capital CDF. Its area to the left on the curve is 95%. Just a reminder, VaR where we are here, this is not a two-tailed significance test. I get this question every year. VaR is always one-tailed. We would never use two-tailed deviates for VaR simply because we're interested in the loss to only one side of this distribution. Where there is a loss, worst expected loss, VaR is always one-tailed, not two-tailed. So these are always one-tailed deviates. And the other thing I would just briefly mention is that I'm following my favorite way of doing this notation, which is following Kevin Dowd. And that is I have a negative on the drift, adding the shocked or scaled volatility. And if we just took a negative to this, negated it, we would also get a common alternative way to express this. It's really not that different. We take the mu and we subtract sigma scaled. Now this is more mathematically realistic, if you like, because we're interested in the worst expected loss. And so the drift is positive. And then on the worst expected loss, that would be a negative. And we would get some negative number here, negative 72. More mathematically realistic because we are talking about a loss. But on the other hand, of course, it's common to convert that negative into positive and refer to the VaR as a positive. When we say here the VaR is 72,000, of course, the user knows, we all know that that's referring to a loss of 72,000, which would be mathematically a negative. So mathematically, this is realistic, although this, by virtue of working with it for many years and with learners, customers, and student learners, this is my preferred syntax. That is to say, following Kevin Dowd, who's very precise and has certain advantages. A key advantage in using this is it helps us make fewer mistakes, believe it or not, because we can make adjustments to this, many adjustments. A very common would be liquidity cost. What do we do when we add liquidity cost? Well, if we come down, if we're using this to get a negative, and if we add the liquidity cost, we're gonna be adding in the wrong direction and actually get a false result. And this is a calculation I actually saw GARP do even on their own practice exam. Just convinced me that we don't want to do it this way. But if we add liquidity cost here as an additional cost on a positive value, we're going to be fine. So this is my preferred method. And I do have a small a, you might have noticed here, that's absolute VAR. What do I mean by that? Well, absolute VAR, simple way of just looking at it is that it just means we're including the drift. If we exclude the drift, we're going to get the relative VAR. And so sometimes I use a little small r VAR to distinguish R VAR, A VAR. Oftentimes people are not explicit, but if there's any doubt, absolute VAR is the correct way to do this, and we could think of this as this would be the general case. Another way of viewing this is absolute VAR is the worst expected loss from the perspective of today's initial value, and relative VAR would be the worst expected loss from the perspective of the expected value in the future. But this is the general case such that we could think of relative VAR as a special case when mu equals 0. And oftentimes we're doing a daily VAR, and it's fine to assume that the drift is so small on a daily VAR that it is 0, and there's no difference between the absolute and relative VAR. And that's why on a question that concerns a daily VAR, we don't really worry about the difference. But just to remind that by absolute VAR, it means I'm being very complete and thorough and including the drift here, which is an offset to this shocked volatility, which is after all the risk. So that in my simple example here, confidence level is an input. It corresponds to that one-tailed normal deviate of 1.645. I've also added in here just an assumption about the portfolio. I break it down. 10,000 shares, $100 per share is an initial wealth of $1 million. So could have denoted this W sub 0, today's initial wealth, because this absolute VAR is going to be worst expected loss from the perspective of or relative to this initial wealth. And then my assumptions here, 1% on the expected return or drift, that's mu, and my volatility or sigma is 5%. We do want to be mindful of the period. So these are single period values, and in this case, I happen to be assuming monthly period. Our most common periods are daily, monthly, and annually, but there's nothing that necessarily restricts us to any single period. We just want to be mindful as to what these input assumptions are, right? I have a 5% 1 month volatility here, so in a way that's unusual, right? Because normally, if nothing else, we assume per annum here on the inputs. But I have a monthly here because for the purposes of the next page, I want to scale this to a 1 year and just show you the scaled formula. So here for my single period absolute VAR, which by definition here means a 1 month VAR, 1 period, 1 month assumptions here. So I'm not going to do any time scaling. So per my formula, I'm just going to take negative my mu, and I'm going to add my volatility scaled or multiplied by the deviate, which is a function of that 95% confidence. And here, of course, by definition assumes that these arithmetic returns are normally distributed, and I get 7.22%. If I multiply that by the portfolio value, I'm getting $72,000. That's my absolute value in dollar terms, my worst expected loss with 95% confidence, assuming the arithmetic returns are normally distributed and it is an absolute VaR. Okay, so now let me go to scaling it. And everything here is similar. And again, I varied from that my normal convention of insisting that the input assumptions in per annum terms so that I could solve for a 1-year VaR, in this case meaning I'll need to scale my 1-month assumptions into an annual VaR. So you notice I've added this. My single period assumptions are the same, 1-month volatility is 5%, but now I'm interested in a normal absolute VaR over the next 12 months. And so I have 12 months per year, so 12 is my delta T. So the formula here is going to be similar. My drift, though, is going to be scaled by time. So I'm just going to denote that delta T. Drift scales linearly by time, and then I'm going to add, again, my volatility, my normal deviate as a function of confidence or significance, but I'm going to scale the volatility as well, but volatility is going to scale with the square root of time, and that's per the square root rule. What's the key assumption here for us when we do this? What are we assuming? It's not normality, it's not the distribution, it's IID, independent and identically distributed returns. Under most distributions, justifies our use of the square root rule. However, these two terms here do treat time differently, don't they? Drift is linear, volatility is per the square root rule or per the square root of time. So, not hard to implement this. I'm going to do the 1-year VaR. I'll start over. Negative my return, scaled over 12 periods or 12 months. I add my volatility, scaled by the normal deviate, and in turn, or multiplicatively, also scaled by the square root of time. And now I get a 1-year absolute normal VaR, if you like, 16.5%, which of the portfolio is just shy of $165,000. It's absolute, so really it's the worst expected loss relative to our initial value of 1 million. Okay, so what is one weakness of assuming that the arithmetic returns are normally distributed? Well, here's one weakness. Let me kick the volatility up to 30%, and you'll notice I get an absolute VaR of 158%, and that's telling me my worst expected loss is almost 1.6 million relative to the initial value of $1 million. Wait a second, I can't lose more than $1 million. Here is a key weakness of assuming that the arithmetic returns are normally distributed, and that is that our distribution makes it possible for us to assume we could lose more than the portfolio's wealth. That's the weakness of normal VaR, and so this is the primary justification, as explained by Kevin Dowd, to use a log-normal VaR. So now I'm going back to, this is the third use case, single period, where I'm going to still use an absolute VaR, but the only difference is now I'm calling this a log-normal VaR. And the key difference here is in the normal VaR, where I assume that arithmetic returns are normally distributed, here I'm assuming geometric returns or the log returns are normally distributed. That is to say, here's our log return. I'll just say P of today over PT minus 1. That's our geometric return, our log return. That itself we're assuming is approximately normally distributed. What's the advantage here? Well, the advantage here is that this asset price will never be non-zero under this distribution. So we can't end up with that result we just ended up before. No matter how high we dial that confidence, under the log normal VaR, we're never going to have a worst expected loss that's greater than our current wealth. Okay, so how do we get that? Well, let's see if our geometric return here is the natural log of the, I'm going to use P asterisk over P. So that could be tomorrow's return over today's, or it could be today's return over yesterday's. That's our geometric return. And so that's equal to the natural log of P asterisk minus natural log of P. Natural log of P asterisk is equal to our return, our geometric return plus natural log of P. If I exponentiate both sides, right, that liberates my forward price to be a function of this exponentiated. So I have E raised to the geometric return multiplied by, right, if I exponentiate this, then I'm going to have E times this circle multiplied by E times this term, which liberates the P. So I simplified this side to E raised to the geometric return multiplied by the price. And then my A VaR, my absolute VaR, is going to be equal to P minus P asterisk, right, which is P minus E raised to the geometric return multiplied by P, which equals P multiplied by 1 minus E raised to my geometric return. And that's my solution, where my geometric return, P1 minus E, raised to this geometric return here, is mu minus sigma z. So that in percentage terms, this right here is my log normal VaR, and if I multiply by P, then I get it in dollar terms. 1 minus E raised to the quantity, mu minus sigma times Z. So I'll apply that now here. Although that last substitution, right, I have the geometric return, and I am being faithful to the mathematical loss aspect, which is, right, I have a geometric return that is normally distributed, so the mu is a positive drift minus my worst expected loss. So I am expecting a negative number here and treating this geometric return as normally distributed. That's the difference. Previously, I treated the arithmetic return as normally distributed. Okay, so given that, right, I'll come in here, and now I'm doing a log normal as opposed to normal. I'm saying 1 minus E raised to the quantity, my mu, minus my volatility scaled by my deviate, 6.97%. How does that compare? Let me go back to my normal one. I had a 7.22% on the where I assume the arithmetic returns are normally distributed. Here I get 6.97%. And let's see. Remember previously on the normal, if I kick this up to, let's say, 40%, well, that's single period, so that's not a good example. So let me do that when I get to, on the next case where I scale at 12 months. So here, same thing, log normal, but now I'm going to take the 1 month VaR and scale it over 12 periods or 12 months to 1 year. And the formula is exactly the same as before. We're going to, in percentage terms, we're going to say 1 minus E raised to the quantity mu, but this time we're going to scale the mu by time, and we're going to subtract volatility multiplied by the Z deviate, and we're going to scale that by square root of time. That will give me the time scaled absolute VaR, and so let's try that. 1 minus E raised to my drift, but I'm going to drift the one month over 12 months. And then I'm going to subtract my volatility multiplied by my deviate multiplied by the square root of the number of periods, 12 months in a year, close parens, 15.2%. So that's my 1 year log normal absolute value at risk, which I have to update that because this is a log normal absolute value of risk. And now I can test this idea before. Now compare it to, if I go back to the 1 year normal VaR and we kicked the volatility up to 30%, we got a VaR that exceeds the wealth, that awkward result. Here, if I kick it up to 30%, my log normal distribution is taking effect. It's not greater than the 1 million, and I don't think it ever could be, right? Even if I kick the volatility way up, I've got a limit on the absolute VaR under the log normal, where again, we're assuming that the geometric returns, that is the log returns, are normally distributed. So finally, let's take a look at an actual practice problem. This is GARP's 2007 practice paper, part 2. And it was only question 2, so it was very early in that practice exam. And I think I've abbreviated some of the verbiage here, but here's the basic setup. A risk manager is estimating the market risk of a portfolio using both the normal and log normal distribution assumptions. The manager gathers the following data on the portfolio. Annual mean is 15%. Annual volatility is 35%. Current portfolio value is 4.8 million in euros, and there are 250 trading days in a year. If you're looking at the actual exam paper, I think it was 252, and I just rounded this to 250. You could see either assumption. And the question actually was a little more difficult than this because it does some 1 day and 1 year comparisons. But nevertheless, the question is representative because it required us to do both normal and log normal VaR and also to scale it over time. So just to put it here, I'll show you here in Excel the solutions. And you'll notice previously we scaled from 1 month to 12 months. So we scaled over, we expanded the time horizon, and here we're scaling down. We're going from one input assumptions, how I like to see them per annum, right? Volatility 35%. We like to be able to assume that's a per annum assumption. However, the question is asking us for, although I'm not showing you, part of the question is asking us for a 1 day VaR. So, right, we're gonna have trouble if we don't get our minds around or don't get a grasp on the time scaling that's going on here. We're given assumptions for 1 year, but we need to compute a 1 day VaR. So my delta T here is 1 divided by 250. Right? If I were going from 1 day to 1 year, it would be 250 days in 1 year. I'm scaling down, so it's 1 divided by 250, or in decimal 0.004. That's what I'm going to take the square root of that when I scale the volatility, and this is the fraction that's going to be used to scale time. So if I just do the log normal VaR, let me start with that one. I'm going to take 1 minus, I'm going to exponentiate my annual return, but I need to scale that down. I need to scale that from 15% down to 1 day, so I'm multiplying it by 1 over 250, or multiplying by 0.004. And then I'm, in this case, with the log normal, I'm subtracting my volatility multiplied by my deviate, function of 95% confidence, and of course my square root of my delta T, 1 divided by 250. Square root of that 0.004, again, because I'm going from 1 year, 35% down to 1 day. And I get 3.52. That's my absolute VaR or my log normal absolute VaR, where I've assumed the geometric returns or log returns are normally distributed. And then if I want to do the arithmetic or the normal VaR, probably the one that most of us are a little more familiar with, I just go right away to my negative mu, multiply directly because it's linear to the delta t, and then I'm going to add my volatility multiplied by my normal deviate or quantile, scaled by the square root of rule, but this time scaled down from 1 year down to 1 day, and I get the slightly higher value of 3.58%, which is 35,000 as a percent of this portfolio, which really should be, if I want to match that question, I didn't update it, should be 4.8, and it's not really, I'm showing in dollars, so if I want to just switch that, make it consistent, I'll switch to dollars there. So that's an application of that problem where we've now done, in this video, we now covered a lot of the basics around VaR, right? In sort of 2 dimensions at least. We've covered the distributional assumption about which return is normally distributed. So we've got log normal versus normal. We've clarified why we're going to extra trouble to define this as an absolute VaR. That's because we're including the mu. And we've generalized the formula to scale over time, either scale from a period to multiple periods, scale up, so to speak, or scale down, for example, from 1 year to 1 day. So I hope that video is helpful. And if it is, of course, subscribe to the channel and you'll get notified of my next video. Thank you.